We're often asked, what's the difference between QSAR and imputation models? So I'm going to explain how the methods differ, their advantages and disadvantages, and when each approach is applicable. QSAR stands for Quantitative Structure-Activity Relationship. In other words, QSAR models capture how differences between chemical structures relate to differences in their activities or other properties. They work by calculating features of a compound structure, or descriptors. QSAR models are built using statistical or machine learning methods to find correlations between the descriptors of many compounds and their experimentally measured values of a property. Multi-target methods can build models that predict several experimental endpoints simultaneously. Once built, a QSAR model only needs the chemical structure of a new compound to predict its properties. This is ideal for assessing many new compound designs to choose the best compounds to synthesize and test experimentally. For example, for virtual screening or in combination with generative chemistry methods. Imputation models are quite different from QSAR. They use both chemical structures and experimental data as inputs. They learn from correlations between compound descriptors and measured data, and between measurements of different experimental endpoints. This approach can gain much more information than QSAR, even when data for many compounds and endpoints are missing. In other words, it can use sparse data. To make predictions using an imputation model, we can input a compound structure and any data we have already measured to predict the results of experiments we have not yet run on that compound, thereby imputing or filling in the missing data. And imputation can be applied to an entire matrix of compounds and data. So why is this relevant to drug discovery? The data we have in drug discovery is very sparse. We typically have plenty of data for early, high-throughput, low-cost experiments, such as in vitro biochemical activities or simple physicochemical properties. But as we progress downstream to more expensive, lower-throughput experiments, such as phenotypic screens or in vivo studies, we have less and less data. Of course, these later stage experiments are the most valuable for selecting the best candidate drugs. But these outcomes are impossible to predict using QSAR models. This is because they're very complex, often being determined by multiple factors, including target activities, ADME, and physicochemical properties, meaning that an enormous amount of data would be required to dissect these complex relationships with chemical structures. And of course, these experiments are those for which we have the least data. However, the data from the earlier experiments contain very valuable information with which to predict downstream experimental outcomes. And imputation methods can leverage these data to make much more accurate predictions than QSAR models by filling in the missing values. That, in turn, enables us to make much more confident predictions of the best compounds to progress, saving time and money while improving the chances of delivering a high-quality candidate. And it's not only about making more accurate predictions. Building an imputation model captures information about the relationships between different experimental endpoints, giving us additional valuable insights. The relationships between experimental endpoints, revealed from the complex, sparse data by an imputation model, can help to identify mechanisms of action and adverse outcome pathways. The models can also use this information to suggest the next experiments to perform that will generate the most valuable data to make even more accurate predictions. This active learning approach maximizes the return on investment for your experimental resources. And the model can identify measured values that are highly unlikely given all the other data in your data set. These outliers reveal valuable new opportunities that you may have missed due to missing, uncertain, or incorrect data, such as false negatives. So in summary, QSAR models are great when you wish to predict early properties of new compound designs and ideas to prioritize compounds for synthesis and testing. Imputation models are most applicable when you have a small amount of experimental data for your compounds and want to use these to make the best decisions to progress from concept to candidate faster and cheaper.